the organizers to be able to present here some stuff. And I'm very happy that I will be talking about thermodynamics just here, because my adventure with thermodynamics started this way, that Jonathan Oppenheim, who worked in gravity, somehow wanted to do quantum information, came to our group of Gdansk, but also at the same time he was a postdoc in Jerusalem, so he was like 3 months in Gdansk, 3 months of Jerusalem, and hopping this way. And these first 2 years, 10 years ago, we have just started this research on thermodynamics and quantum information, and did it for a couple of years, but people at the time were not interested in that subject. So we also couldn't solve some problems, so we just stopped. And now there's much more interest, and I will tell you first about some older stuff, and then we'll, which is a good warm-up, and then we'll come to the most recent developments. I didn't prepare some systematic full picture, just because I'm in it and it's being developed. It's not, maybe it's not now time to really, to work on it systematically. It's better to really go on and develop for a while. So I just will report stuff that I was doing, and maybe a little bit of stuff of other people. So at that time in 2001 and 2, what we did was thermodynamics for kids. Thermodynamics for kids. Okay, so what's thermodynamics for kids? So it's essentially based on Landauer principle, but view it from a converse direction. So normally, Landauer principle is that to erase bit, this amount of work is needed, which is that if I have I will use cat notation for bits. I'm sorry to computer science people. So suppose I don't know. So suppose I don't know whether my bit is in the state 0 or 1. Okay, and I want to reset it, or I want to make it to be just 0. So to this end, the Landauer principle says you need to spend this much of work if you have ambient heat bath. But you can also plus. So let me write this plus. But you can also do the converse. So you can say, if I have this, and I have access to the heat bath of temperature T, then I can draw this amount of work. And usually when in this old literature developed by Landauer and Bennett, but started with Szilard actually in 20s. You do it by the Szilard engine, which is one molecular engine. So you do such a stuff that you have here a piston, and you have one molecule that is here, which means that you have this bit here bit is 0, here that bit is 1. And then you simply, once you know that the particle is here, you let the piston move this way, and you draw this amount of work. That's very speculative, because a gas containing of one molecule is maybe not something which we very often see. So there are, of course, other many versions of these Szilard engines. And later I will not refer to any particular models of realizing this, but I will provide some really well-defined framework. But for a while, when we started doing this, we just took this as a basic principle. What I can do if I have a pure bit and I have heat buff, I can draw this amount of work. And then already it was noted before by perhaps Bennett and Charlie Bennett, and we are also inspired by Vlatko Vedral's paper, who tried to combine Landauer's principle with entanglement, with correlations. So you can try to think of some more complicated system than just one bit. So you can just say, oh, suppose I have two bits, and suppose for a while, suppose they are correlated. So either we have this situation, or we have this situation. So we don't know where is the particle, but we know that either it's in both boxes on the left or in both boxes on the right. So then the full state is such state. Yes, either both left or both right. And then you can say, well, so I do not have this. So what I can do in order to apply again this principle? So I can simply make some reversible transformation here. So it will not cost energy. So you can just apply control not, which will bring you to such a state. So you don't know where is the first, but you will know where is the. So in one box you have then you don't know where is the particle, but in the other you know precisely. So then you somehow distilled from this mixed state, you distilled one pure bit of value 0, and then you can draw this amount of work. So in our early research, we just said, well, so if you have a state, let's try to see how much work I can draw by using this. So we imagine we have heat buff, big heat buff. We have our now arbitrary state rho, let it be even quantum, which is in this case not very relevant. And then the question you can ask is how much work. But of course, how much work by this principle? So actually the equivalent question is how many pure bits? How many pure bits? So if you ask like in this way, then the heat buff is really not needed. You just take your state, or maybe it's many boxes, many bits, and you do something with it. You try to obtain some pure bits, and then only you stick to the heat buff and you use this principle, and you get your work. So what we actually were doing was the following: manipulating on states with no energy whatsoever, no work, no such things, just manipulating. So some manipulating on pure on states, right? And then only stick it to the heat buff when we already have nice output. So what we were actually doing was, what is manipulating with? So let us see that this, if you have some completely mixed state, you don't know what is the value of the bit, then you cannot do anything. It's completely useless. So what is useful is when you know something. So what is useful is information. So heat buff you can think is something where you have energy, but you have lack of knowledge. And then the state is useful when it has some information, when it presents some information. So or where you know something about it. And therefore, information here was the resource. If you have information, you can draw work, right? So what we actually are doing is this. We're manipulating information. You get some state that is not of this simple form. It's not of this simple form, but maybe it's more complicated, maybe even much more complicated. So we start from raw, and we are manipulating with some class of operations, which should be clever. For example, the class of operations shouldn't allow you to bring in this state. So, for example, if you consider just reversible transformations, for example, unitary transformations. Of course, unitary transformation preserve spectrum. So if you started from maximally mixed state, you will end up with maximally mixed state. You cannot increase purity. You cannot increase amount of this nice resource. So therefore, you consider some class of operations, which will include unitary transformations and otherwise just removing systems. And later I will say more on that. And you get something. So you start raw in, you get raw out. Okay? And then you are interested finally how many pure states you have. So what is now, so to summarize what this thermo for kids is, it is information theory, which is manipulating of information by means of some operations, times kt ln 2. So we do some information theory, we manipulate with states, and finally, by multiplying with this, we say we were doing thermodynamics. So that's this thermo for kids. And this my first part of these lectures will be about this. And just to see how it developed, so our first paper looked the following. So it looks like this. That's the paper. That's the some page. And then we have many formulas, and everywhere was KT, KT, KT. That was just first paper. Then we realized that it's enough to write KT in the abstract or in the introduction. Right? Maybe also in the conclusions. Then we said, well, anyway, our next papers were no KT whatsoever. But then, because finally we wrote review, and so no KT, and this review, so that's review. So there we multiply all these times KT, so that people knew that we did thermodynamics, so that nobody later will multiply with KT himself, but just we did. So yeah, so that's Thermo for Kids, which will be very useful for getting ideas, for getting to know what should be the thermodynamics for adults, which will be the next part of my lectures. But already now I will announce what were problems, where we want to go after doing this. So right, so that was this thing. Mm-hmm. Maybe I will switch on some references. So I put here some relevant reference for this early. Oh, where is that? Ah, yes. So these first three are the reference relevant to this first period. And then, so that's this Thermo for Kids. Then there will be references here, starting from here. That's Thermo for adults, but of course you see that it's not chronological. So there is this. I don't know much literature on this thermodynamics in quantum regime with small systems, because you see here, this was about single beats, such things. So this is a very really small system. where you have non-trivial Hamiltonian, not unlike here. Here we do not have any energy levels for the systems. Yes, no energy whatsoever. So there is this paper by Robert Aliski, which I think is very relevant. But I will talk later about this. So here is this starts thermo for adults. So right. So by doing this, let me emphasize one thing. That this already, what is nice thing about this, that this is some resource theory. So you have some resource, which is, so actually it is resource theory. So the resource theory is, this notion started to be like in fashion because of entanglement theory. So people realize that entanglement is a resource that you can manipulate, that you can distill, you can form, you can just play with it, and you have some class of operations, natural, which will not increase entanglement. So, and at that time, entanglement theory was very fashionable. But this thing is extremely, like the simplest resource theory you can imagine. What does it mean, resource theory? This means that you have some states that are valuable, and you have also some states that are not valuable, and they are freely, you can have free access to them. You can have as many systems in these states as you want, and these states you have to count. You are given, and then you can only manipulate them. You can maybe change them, maybe degrade, but you cannot bring in. Okay, and then you have operations you can perform. You have operations, but the operations should be suitably designed so that they do not bring in these states. Because you can imagine an operation where you bring in a new particle in a valuable state. Then your theory is trivial. You can do everything. So, but if this operation can only bring in these free states, then once you have, say, one system in the state, valuable state, you cannot really do anything. So you cannot really achieve any state. So in this case, operations, this free state is just maximally mixed state. Maximally mixed state. So this is a state that is clearly useless for the purpose of drawing work, for example. But also you can think that this is an equilibrium state for a system which is trivial Hamiltonian. If you have just zero Hamiltonian, no Hamiltonian, or just fully degenerate, then this is the equilibrium state, maximal mixed state. So this is like saying that more generally it's saying that heat bath I have for free at a given temperature. But but here, as I said, this will be this information theory times this. So I'm now saying only about this. So there is no energy, no heat bath. We can just think of states, and this is the maximal state. Valuable state is anything that is not like this. Yes, anything not free, not maximally mixed. And operations are those that preserve this. So operations were unitary and bringing in free resource. Okay, adding maximally mixed state and removing, and just removing systems. Removing systems. Okay, so what was nice about this is that we had some resource theory that was kind of thermodynamics, very toy, but it had a flavor. And then we thought, but thermodynamics itself is really a resource theory. We have fuel there. That's a resources, yes, in the economy, fuel. So thermodynamics is even much more resource. This is very toy resources. This is very abstract. Yes, in thermodynamics we have some very concrete resources. So it should be really there should be a resource theory behind thermodynamics. And we wanted to create one, but we faced a problem, some problems. So want like true thermodynamics. To be resource theory, which would be about state manipulations by means of some operations, relevant operations. So what is the problem? The problem was that, which we faced at that time, was that work was not about states. Work was about changing Hamiltonian. So for example, you may find such formulas for work. So you go through some path, you change the Hamiltonian, and that's the work that average work that you performed. So that's one thing. So problems. Problems. Work is not about states. Yes, it's about Hamiltonian. About Hamiltonian. Second problem was that it was not clear what should be the class of operations. What should be class of operations? And what we knew for sure is that the heat bath will be a free resource. So Gibbs state will be a free resource. So that was not a problem. So Gibbs state free resource. Okay, this we knew. But so one thing of which we wanted to develop is the following. Look, we have some nice resource theory that is looks like thermodynamics. Why not to recast thermodynamics as resource theory, but just to understand it better, with no further, just to understand it. It must be such a thing. So let us find it. There is another issue, but there is another goal where this resource theory may help, namely to build a thermodynamics for a microscopic systems. In a
maximal state, the coefficients of the state are all equal. Right?
Yeah. Yes.
But in a thermal state, it's not the case.
That's true. But for a trivial Hamiltonian, it is the case. So precisely, this thermo for kids is of systems which have trivial Hamiltonians.
Or infinite temperature.
Yes, but like in view of further developments, it's more natural to think in this way. Actually, that was we at the time we talked to Robert Alicki, who is really good specialist in thermodynamics, and we also were talking about these possibilities. He didn't like this this infinite temperature, and then we indeed wrote a paper where we did this argument that from pure state you can get kT logarithm of 2 using a model of degenerate two-level system in a pure state. And then he was happy, because otherwise he didn't understand why we are able to multiply with kT. And then after this paper he was just happy. Yeah, good. So at least there is a model which is not like one particle gas. It's just two-level system with trivial Hamiltonian. Good. So another goal. So one problem is this. So we want thermodynamics system, and the other problem we want thermodynamics of a microsystem systems. What do we mean? I mean this, that we have here heat bath, and here we have some microscopic system, which is, for example, just two-level system. Just two-level system, or just a small system. So normally, in thermodynamics, you have this. It's really good for macroscopic systems. because there are averages, you have average work, you have such quantities, which are good when you have some ensemble. What about if I have just a single qubit, two-level system? So, when you start to think about this, you have many problems. How to meaningfully translate some thermodynamical quantities to this paradigm. We have here a small system, and you have just one system. You have many of them. You can already think it's something like a gas, yes? But you have just one particle. It's not anymore a good gas. You cannot use all the prescriptions that give you the statistical physics for from textbooks. Although we want to keep large heat buffs, so here we can use statistical physics. But this we want to have to be small, and this interacts with a heat buff, and then we want to meaningfully say, oh, we have drawn some work. So, as I said, there is this paper by Robert Alitsky in '90, where he considered just arbitrary system here and defined computed work, showed a formula, and got Carnot efficiency. But that was not fully satisfactory because he used average work. And while you would think that work should be something clean, so in our dreams, we thought, work is some like mechanical energy, it's the clean energy. So the heat is some energy that you have also probabilities. You don't know on what level you occupy. But but work should be something that is clean, and then therefore you also see this opposition between something. In this term for kids, you had a pure bit that was valuable, and a mix that was not, and then you have heat buff, not valuable, and then you have this performing work is bringing a clean energy. So when you use this average work, then you are not sure, because then you still have probabilities. What does it mean? Maybe now I tend to think in a different way, but it's good to think about it. So yes, so these two turn out that they if we recast thermodynamics as a resource theory, we will be able to meaningfully talk about micro systems. And there is one beautiful paper already in 2000, which it should be the first paper here. So I should add here. So it's just later full. So that's the really pioneering paper, completely for many years completely forgotten, where they did this thing. I asked here, what should be the class of operations? In that paper they did. They defined class operations, relevant operations for thermodynamics for adults. So it was 2000, right? What was still lacking was, how about work? Okay, and so now there is so now there is we finally managed to combine our dream on this of thermodynamics as a resource theory with the fact that we have class operations by Yancing, which I later tell you. It's just some thing more complicated than just our term for kids. And okay, as a warm-up in this paper with Fernando Brando, in this paper, yeah, we asked a question: what if you have many copies of some state and a heat bath. But now you have full thermophore adults. You have Hamiltonian, okay? So with a Hamiltonian, and then you want to get other number of copies in some other Hamiltonian, with maybe some other we consider the same. But so that was a warm up, and the answer was very beautiful. We expected, but namely the answer is the following: that the ratio is the optimal ratio that you can get is the ratio of a distance of these states from an equilibrium state. So it's relative entropy distance of rho from a Gibbs state and so actually here the story is that if some of you yes. Thanks. I will later tell much more about this, but today I will repeat things. So good. So we are given some n systems in state rho, and we want to get the Hamiltonian H, and we want to get output m systems in the state sigma. Right. So it's given. We're asked to do that, and the question is how what can be this ratio?
So what would it be in the case in the quantum thermodynamics for kids, where you wanted to get pure state sigma?
Yes, as this the main goal of Thermo for Kids was indeed get first of all do we have some so for Thermo for Kids that was 0, right? No Hamiltonian, and also no Hamiltonian, and then yes, mainly we are talking about getting here pure state. That would be drawing more, but of course we formulated it more generally. Same vein like here. We start from rho, we want to get sigma, and in particular, we may consider this to be pure, which then you can multiply with KT, right? So this is it's similar like in entanglement theory. If anybody it's interesting this history. In entanglement theory, people first answered some asymptotic questions. I have many copies of this state. I want to get many copies of the other state. What's the interconversion rate? And then people start to say, maybe I have this state single copy, and can I go from this state to that state? So this is usually called IID because these are independent. So that's called this IID. And in this picture, what's beautiful is the reversibility. So this is like in thermodynamics, where like Carnot cycle is reversible, and that's precisely that's the manifestation of it. But this is not in a sense, it is microscopic, but in a sense also not, because you are given many systems really. So now the next step was to do a so-called single shot. So we have these two. Where is this? Where put? Here. So we'll use these two notions. So you have single shot, which is that is single copy, but it's or IID, yes. And this is very basic. From this, you usually can derive back these results. But historically, often people started from these, even though they seem to be difficult. But and then later do single shot. So single shot is about, can I go from this to this? That's a single shot question. Can I go, right? Good. So where we are now, okay, we consider transitions. We now can consider even these transitions. Now the answer will not be anymore so simple. But still we don't have work. We don't, yeah.
What is this
Oh yes, it's relative entropy. Relative entropy. So it's. Let me define it. Yes, yes. So it's relative entropy. Maybe raw. Some other thing. Is just trace raw log raw. So it's relative entropy. Entropy. Right. So,
Is it trace raw log sigma?
Trace raw log sigma. Trace raw log. Trace. Yeah. Yeah. Sorry, because I didn't want to put this sigma. Yes. So that's a prime here. Seems okay. Yes. Sorry. Is that okay, or because I may be very wrong in science and everything? Trace raw log. Yeah, because it's like, or yeah, it's like. I think it's okay. Or maybe it's this thing. I cannot. No, it should be. I think it's this thing. I think it's this way. Yeah, because it's good. So why it's nice actually, because in this early papers by Robert Alitsky, which I mentioned, and it appears, this quantity appears too, and essentially in a dynamical picture of going to equilibrium, it tells. Also, it uses this. Yeah. Here, and here is a Gibbs state. Suffix. A beta is inverse temperature. Sorry, I just want to say that this is the Gibbs state at a given inverse temperature. So beta is 1 over kT. Yeah.
It depends on which is your state, which you get for free.
Yes, so here the free state is just the Gibbs state at a given temperature, fixed temperature. Like we have one ambient temperature, because if we have more than we could draw infinite amount of work by just running kernel energy.
So we go from a heat bath with infinite temperature in the kit game?
Better I would say, no, in kits we have T, also T, because I multiplied with KT. But the Hamiltonian was trivial. And that's why the Gibbs state didn't depend on the temperature. Right? If we have just Hamiltonian 0, your Gibbs state is identity divided by dimension without irrespective of temperature. But here, if you have a non-trivial Hamiltonian, then of course it depends on temperature. And that's why here we should put this free state has this index beta, while there I didn't need to put an index. That's free states was. So that's why it's good to think about rather trivial Hamiltonian than the infinite temperature, because I have T there. I multiplied all our papers by KT. So yes.
So these Hamiltonians are the same?
Yeah, in that paper we had the same Hamiltonian. We can also further have different Hamiltonians.
That arrow represents the unitary transformation. What is it?
You mean what class of operations?
Yes.
Okay, so later I will define it. It's okay, I can tell. It's unitary that commute with the total Hamiltonian of the system and of the heat. Later I will repeat it, but to conserve energy. Yes, exactly. So there we didn't need to do that because we only operated on the states which have trivial Hamiltonian. So anything conserve energy. There is no energy in the system. There is only energy in the heat bath. And here I have to already be more careful. And that's what was in this Jantic paper, this et al. In this paper, they propose this class of operations. The unitaries that conserve energy. Yeah. Right. So how much time do I have? Good. There were some questions also. No, good. So, right. So that was warmer, but still no work here. Yes, it is just about state-to-state transformation. So still there was a problem how to really have work, and resource theory. So one solution was proposed one solution was proposed in this paper. With myself, with Jonathan, where we simply said, okay, since we anyway ultimately want to be able to deal with microscopic systems, and we want that work is something really certain, so let's make, and we also want to have resource theory, so we want to talk about states. So we say, we say a work. I do work. So when I have a work system. So I would have some heat bath system. So heat bath is like reservoir system, and also work system. And in this work system, we propose that work is simply going from one excited state, pure excited state, to another pure excited state. So essentially, that's doing work, which is this thing. Sorry. So when we no, it's not doing. It's okay. This is the work that I usually prefer not about performing work, but about extracting work for some reason. So to me, this will be how much work I extracted. And I extracted from some heat bath this amount of work. Where there are parallel papers by Paul, or maybe even earlier, by Paul Skrzypczyk and Sandu Popescu and other collaborators, and where the work is defined more closely to what we think is work. So work is raising some weight. So then you simply consider some system which is like infinite degree continuum with continuum spectrum, which is just precisely the Hamiltonian of the weight, which is so. At the time we had problem with this approach, but now it converges. So the approaches converge, and they show beautiful, they are beautiful, I say, complementary. So they show the same. Finally, so I will later in my maybe last part of my lectures, I will also talk about this other approach a bit, but not sure whether I'm fully competent. So okay, so this is the definition of work, and then we are very happy because work is about just state of change of state. So now everything about the state. When you want to know how much work can I draw from my state rho and a heat bath? Okay, so you add here some system, and then you ask, okay, I don't care what happened here, and finally I want to get this up. By what? By my class of operations. That was defined in this paper by Jansin and collaborators. Okay, so then we can look. Now it's about change of state. So I finally can just ask the question. I go from rho to sigma. If I know the answer to this question, whether I can go from rho to you give me some rho, give me some sigma, and I should decide, can I go by my class of operations? If I solve this problem, then I can also solve the problem, how much work can I go from rho? Because then I consider this thing as my let's say rho initial, rho final, right? So I say this is my rho in, and I want simply to transform it into my rho out. Well, I dropped this system, but if you want, you may keep it and require that it is a Gibbs state. So that's the same, because Gibbs states in this game are for free.
So you don't keep track what's going on in the heat vector, right?
Yeah, I don't.
It stays as a heat vector.
It will be influenced, so somehow this big heat buff will be final in some other state, which I don't care.
Does this stay in the same state all over the?
No, it will be affected.
And why do you use additional system that will work instead of using just state of system itself?
Just to, because yeah, just to know that I did this amount of work. Because if I have system itself, I don't have this clear division. I can't say I did. How I can compute the amount of work that I did?
But you cannot use the state of system itself.
Yeah, finally, ultimately, we will use it. Just it will be the whole system, but it's good to have it divided, because then I see, this is my amount of work going from here to there. It's like when you have like a gas in a container and a piston. So what does it mean, drawing work? This means that you have lifted some weight. So that's your system, where you just see, this is the work I have drawn. So usually it's good to have some separate system that will store the energy at the time. Sorry.
Did you say what is your cost of operations? Or
I did. But I will be repeating it. So it's all the unitary transformations that commute with the total Hamiltonian. Right. Also adding for free Gibbs state and removing particles, but that's a trivial part.
the total Hamiltonian of everything, including the Gibbs state?
Yes, total Hamiltonian, so total Hamiltonian of the system, of the big reservoir, of this, and of this.
But there are also couplings between the systems.
But these couplings will be taken, they will be cared just by this unitary. So the unitary commuting with this will just will be just an effect of these couplings. So later I'll tell more about this.
Is it supposed to assume that the resource doesn't change? That's the first point. And second, that the energy levels are equally spaced? They're discrete level. You can't have a level smaller.
Yeah. So therefore,
Uniformly spaced.
yeah. So I mean,
That's a supposed to state, right?
but they have. I think ultimately they have these continuous. So then you can have change. You have arbitrary changes. In this model, we just adjust the system. If we know how much, we just adjust the system. So you can, for example, compute how much work you can draw, and then you just stick. Even in this approach, it's enough to have just two-level system of work system. You just, but you have to have very the energy difference should be tuned to what you know you will obtain.
But there's no limit. You're not saying that there is a smallest delta P which you can have. Is that
No.
so you're not making any restriction on how small delta?
No. So I can draw, if I know I will draw only a very small amount of work, I just in this approach I will just stick a two-level system with a very tiny.
Because they came up with a quantum efficiency. There's a minimum value below which you cannot go. So that's
Yeah.
what they came out with, that there is a limit on delta P.
Okay. Maybe I should understand more the papers. Yes, definitely. Yeah, that's I think that now I'm very much prepared to understand these because we started to converge. So we get the same results, similar results, or if we get different, then it's very clear why they're different. So yeah, thanks. Yeah. So as I say, we are in the middle of this. I don't see the full picture. What is really settled very well is this resource theory, but there is a big job of trying to see how it's related to more standard approaches and so on. Right. Good. Good. So, where's my time? Right. So we have deterministic work. So this work is deterministic. Yes, it's very well defined. So now we have all ingredients. So we know what's class of operations. we have this, of course, class operations include adding free states. So we know free states is Gibbs. And we know what's work. Okay, that's work. And then as I said, so in this paper with Jonathan Oppenheim, we answered this question for states that are diagonal commute with Hamiltonian. For the states that do not, we have partial results only. So for states, like call them quasi-classical, so commute with Hamiltonian. So some people can say that they are not really classical because Fock states are not classical. Classical states are coherent states which do not commute with the Hamiltonian, while Fock states do commute by their extremely quantum. So it depends on your perspective, so on the point of view. So for this purpose, they commute with the Hamiltonian. One can think of them to be classical. So what do we do? So we have answered this. So we know when from rho to sigma you can go to sigma, and then we can apply it to our definition of work. So we can now, so using it, we can get how much work I can draw from rho. Of course, we have in mind that we have this heat buff. So we always take rho, add a heat buff, and then get work. So that's one sort of question. Then you ask questions that you usually in thermodynamics you wouldn't ask. Well, maybe you would, but it's rarely more. Okay, you ask when you do some in Carnot cycle. You perhaps ask it. So how much work I need to create this state out of nothing, out of a Gibbs state. And then you have most like general question. I have state rho. How much work should I add to go to some state sigma? So these are given, and I ask how much. So maybe I even get work. Maybe I can get work. So of course, the thing is that once we get this, these are some special cases. Why? Because now work is about just state change. So if I know how have transformation rules for states, these are some special cases of this which can be answered. And so this will be, as I said, next portion of papers will do. I will deal with Thermo et al. In this picture, so in the resource theory picture, and I will present this criteria and answers to these questions.
So can I?
Yeah.
This second operation, from work you create a state.
Mm-hmm.
From energy you create a state.
And no, you usually have some system in a Gibbs state, and then you want to change its population so that it becomes some more interesting state being rho. So yeah, so you don't recreate a state, but you want to change it, and by this, yeah, I say that. So you have work which is like you pay for that, but you do not pay for any Gibbs state, and you can like add here as any Gibbs state that you want of any systems. That's free in this theory. Yeah. So the last thing that I hope to just to tell about is related with different definitions of work that are also sensible, more close to traditional approach, and what is nice, they give the same answers. To not fully, there are still some details that there is some work in progress to understand fully the difference, but roughly the answers are the same, and that's very nice. So what's another approach? It was parallel approach to the paper by us, by Johann Oberg. Okay, so that's this paper. I see it, but you do not see it. Johann Oberg. So, good. So that's this paper, where he defined. I will maybe not tell now exactly. I'll just roughly tell how he defines it. So he simply says, okay, if I have a system, and if I move a level up, and the system was populated, then I had to I have to be prepared to put this amount of work, right? So, and vice versa, if I, so essentially he says this, I do some sequences of changing levels, changing energies of the levels, and because I had some probabilities, then I have some paths of possible I get work, I lose work. If I raise the level, I lose work. If I lower it, I gain it. So then you have some paths of getting work and losing work. And if the most likely paths are give the same amount of work, and if it is positive, then you can meaningfully say that you drawn deterministically some amount of work, even though it has some spread. But you are sure that, for example, you up to some small probability of failure, you are sure that you are above some, that your work system is above some, started from, say, this energy, and then it's above some energy. So that's an approach close to this more traditional, where you simply work is change of energy levels. And Johann what he did, he provides this. He answered this question, and the answer was the same as our answer, right? So this means that this resource theory indeed is compatible with traditional thermodynamics. Of course, we knew it also from some other somehow in many other ways that it should be, but it's once you know here the answer, it by no means gives you the answer here. So to give if you know this number, to get the protocol with these changing levels, it's really completely different work. Yeah. The answer, yes. Right. So the answer is the following. Usually the answer is in two. How I like this, say, single shot approach is different. So I have a single copy of a state. I know what I can exactly get, and then I smooth. So I say, but now suppose I want to tolerate some error. So this smoothing was actually, promoted by mostly by Renato. Is Renato here? No. Yes. For cryptography, quantum cryptography, and later also everywhere essentially. So I will write the answer without tolerance of error, and then you say, and then you smooth. So then you can add some epsilon, and there are some formulas to how to go from exact answer to. So what's an exact answer? So if I have rho, then the amount of work that I can get is the difference of free energies. So it's very familiar, because normally if you have some one Gibbs state with piston here and then the other with piston here, so then you simply compare the free energies and say that's the amount of work I can get in isothermal process. So here it's also the difference of free energies. So minus F out. But the free energy is different than the standard free energy. So standard free energy you can write as a free energy. So free energy of rho you can write as a free energy of a Gibbs state plus the excess, which is the relative entropy distance of this thing. And here I guess should be some kT. Oh, sorry, K. Sorry, must be energy, so kT. Right. So that's the standard one. And while here we have this so-called min free energy, and min free energy is same here, but is kT min relative entropy. So essentially what happens here Okay, this mean relative entropy is something which is defined as I should really now know how much time do I have. Some positive or negative amount.
25 minutes.
25 minutes. Very good. Perfect. So I will even maybe go beyond introduction. Good. So S mean of rho prime is what? Is minus log trace. And here you take projector on a support of rho. And here you take this, I guess. So that's extremely bad, ugly, degenerate quantity, which is, you know, from rho you only take the support, right? So that's much less sophisticated than this nice, beautiful expression. And it's the projector onto, this is the projector, a support of rho is the space spanned by eigenvectors that are have non-zero eigenvalues. So essentially, if you diagonalize the state, then you have here 0, 0, zeros, and here you have some non-zeros. So the projector onto this space is a support. So I should, yeah. So of course, the classical expression is that you simply take. Let me write for commuting case, because essentially we have our expressions are only for. For work distillation is for any state actually. But let me write for commuting states. Commuting case is a sum over. So commuting case. So we have probability pi and qi. So that's rho prime, and then we have for such I that pi is different than 0, qi. Such a thing. So this thing, look, it is 0 if only this is a full rank, suppose this pi are all non-zero. Then this is a 1. So this S mean is 0. So in such case, this term S mean here is 0, and you cannot do like your F mean is the same as free energy of a Gibbs state, which means that because here this is the answer if you don't let me stick to the scenario where you do not change Hamiltonian. Initial Hamiltonian is the same as the final. Later I will elaborate on. But if suppose it's the same, then this means that these are just the standard free energies of the Gibbs state, because this was 0. So you will have no work. So already here you see that you only can get some work from a state when it has some non-occupied levels. And this is very similar to in thermophore-Kitts. So in thermophore-Kitts you had this pure state, 0. From this you got work. And here you had just one level occupied, the other not. And here you have to have some empty levels to get some work. But then you can ask, so how I can get standard thermodynamics when I, for example, know. So maybe that's for later, but later you can also smooth. You can say, but okay, in nature I really don't have such systems which have some empty levels. The levels also have always have some probability of being occupied. But then you simply say, okay, with this probability, so I have some levels that are almost empty, and you say with this probability I will fail. Yes. So that will be the smoothing. We say I allow some probability of failure, and that's the probability of occupying these levels. Okay. So you first have sharp formula, which says you no work if all levels are occupied, and then you say, but it's very unreasonable. If my level, probability that my level is 0.0001, then I shouldn't take care. I shouldn't care. It should be empty for me. So then you simply add some epsilon, and here you add some epsilon, which is the smooth quantity. And later maybe I will have time to talk more about this smoothing. So good. So right. So and then there was so in this paper there was just this thing, and it was already kind of complicated. Yes. Good. So Pi are eigenvalues of this state rho, and Qi are eigenvalues of rho prime. So classically, you think you have just two probability distributions, and you compare them. Quantumly, you have two states, and if they commute, then actually it's like you have two probability distributions, and then you compare here them. Right. It's good that you also ask the questions that were already. That was a new question, but don't hesitate to ask the questions that were already asked. It's good if as many people are together. So yes.
Why does it depend only on the Qi and not on some function of Qi and Pi?
Here is this very mild dependence, but also very strong dependence on PIs. Yes. So I only take. So it's like it depends. It depends in a very crude way on PIs. It only looks whether Pi is there or it's zero, non-zero or zero. So it takes only these Qis for which you had non-zero PIs. So that's a very crude way of depending on Pi. It only distinguishes whether it's empty or non-empty.
No, but why is it such a crude dependence?
Yeah, this I will come to it later. Yeah, this will you will see from the protocol how you really get this work. Okay, and there was the final twist for a while was this? So what about these other answers in this paradigm where you change the levels of the Hamiltonian? That's how you define work. So how about these? So there is did I put this paper here? I should have. So there is the paper by. Okay, I recall there one other author is Renato Vlatko-Vedral, and there is fourth one. Maybe you remember Renato, the fourth author. Yes, Oscar, of course. So that was the only. So that's already full. So alphabetically would be here. Right. No, it would be here, but for a while. But I think. Good. So up to some details that I will tell later. Let me say I still have to digest this result. I hope Renato will help me while we are here. But I know I understand the result at least. Namely, they did they answered these things also using this more standard approach to definition of work. And what's beautiful is that the answer is the same. So and again, knowing this answer and knowing this by resource theory gives no hint whatsoever how to do it in this picture. So I know this answer. I know even this paper, and I said, okay, so for this paper I should make it myself. Just I know what's the result. Just let's forget about the paper and try to cook up the protocol. And I cannot. So I hope before this here lectures I will be able to understand. But no. So now have to either read the paper or just ask directly the authors. Good. So so I hope maybe I will maybe show this more in detail, and I will tell a bit about this thing. And there are still nice big questions related to some interrelations between these approaches. Good. So maybe so that's the end of my introduction, and I maybe will write some table. Now some table. Aha, this class of operations is called thermal operations in this thermodynamics for adults. So let me make this some picture for. So here is thermo for kids. Here it's for adults. So we have here free resource, and here free resource is maximally mixed state. Here is Gibbs state. I should start from Hamiltonian. Here Hamiltonian is 0, trivial, non-trivial. Okay, non-trivial. Operations. So here we have unitary, all unitary. Of course, also adding free states, yes, and removing anything. So here is the same, and here is unitary, but only commuting with total Hamiltonian, total H. Meaning total because here I say H for the system, or H system, but by total meaning everything, also a heat bath and the work. So here is the same, adding free state and removing anything we want. Right, so that's the operations. Anything more? I have something that is what I want to say here. Work. So here work is easy. Is purity is of purity times kT. Yes, amount of purity.
What's the word before purity?
Amount of purity. That's the number of pure bits. It can be. Here I say about bits, but one can imagine some smaller number of work by having some more sophisticated. Maybe it's later I will maybe say. So is this, and here work is. So here I compared resource theories. So I will just put this from our paper, which is what was that? Is exciting. I think eigenstate. It's exciting a work system. Like how to say it? Deterministic, yes. Deterministically exciting worker system. So essentially, that's this picture, right? So also Hamilton. So here you can. So here's non-trivial Hamilton. So you can say like this, and here is trivial Hamilton. So you can just draw like this. Yes, you have like degenerate system, and here is non-degenerate. So here is a difference of levels. Good. So these are two resource theories, and then there is another story which is not precisely research theory because it has different definition of work. So I can maybe even do this. I can do like that, and here say let's say I didn't have too much time to tell it more precisely here. I'll do it later, but it's about raising levels of Hamiltonian and requiring some like some concentration of the distribution of work, or even some not maybe concentration, but being sure that we are above some level, for example. So some certainty, let's say certainty, right? So these are these two approaches. Good. Okay. Sorry. Raising levels of Hamiltonian of the system.
I'm not really following the motivation of the definition of operations. I mean, there aren't very many for a generic system. There aren't very many things that commute with the Hamiltonian. Basically, if there are no degeneracies, then you can rotate the phases.
Yeah, then
So
you need big degenerations.
So why is that interesting? I don't really understand why.
So first, why it can be non-trivial? Because in some generic heat bath, you have a lot of degeneracies.
Right, no, usually you don't, right? I mean, I usually think of a complicated quantum system having no degeneracies except those provided by symmetries.
Yes, you're right. Though on the other hand, yes. So there is some. Yeah, it's interesting to compare it with some maybe many body systems and such things. But indeed, if you take the simplest model is tensor product of many copies of the same Gibbs state. Then you have a lot of degeneracies, and they allow you to do a lot.
There's no interactions.
That's true. Yeah.
Yeah, but in
That's
life
true.
there are interactions.
Yeah. So if you have just you can think you have this ideal gas as a heat bath. Yes. Right. It's just let's just stick to this for a while to be just.
Okay, but then it's then it's a very special system.
Yes, but we are looking. We're talking about ultimate possibilities. So you should ask what I can do ultimately. Yeah. So that one day one didn't come to you and say, look, I have better heat buff. Maybe you can do better. So we have these limitations. These are limitations that are ultimate. You cannot beat them, but also they are achievable by some maybe stupid systems. But
Should we think of the heat path as having continuous spectrum?
You can think like that. If you want to do some particular rho, particle W, you want to do that, you can just choose your heat buff to be discrete, but tuned. But if you want to have some generic heat buff that does this, then it should be continuous. It should really be able to tune to every level spacing that you have here. Yes.
Because you do have a special Hamiltonian, which you could decompose as a sum of Hamiltonians for reservoir, system, and work system. So you have operations in which you can increase the energy of the system, say, and decrease the energy of the bath.
Yeah, these are these non-trivial operations that you can do. There is a question there.
What prevents you, there are two kinds of unitary operations which I can do. I can do the active operations which are basically I just look at the system difference. So what prevents you from just changing the basis in which you describe the system?
I think you for example usually would introduce some correlations between two systems. So John was just said that what's the thing was a particular type of operations that you raise energy here, you lower here. Yes. So then you can maybe finally you can raise energy in your work system. Yes. And and that's what would be your goal. So you have your state, your heat buff, but this is lowered, and then by these transformations you can make this. So it is some finally ultimately it is some rotation. It's some change of basis, but it's important because now my state is excited. Before it was ground. Yeah. So here change of basis is not something for free, because you may increase energy of your system, for example. Maybe you still have some.
It's okay.
Good. But yeah, please challenge everything. Simply, these results are so like elegant that it's there must be some